All right, I'll begin with a word prayer. Dear Father, we thank you for this morning. I thank you for the students. Pray that you just guide our thoughts today, help us to understand tangents and normals and a little bit more about manifolds. And I just pray that you just help these students as they work on this course and others this semester, that they could just do the best each and every day, Lord, for your glory. In your name I pray. Amen. So I started to talk to you guys about what's a manifold last time, right? So, the natural question is like, what's the history of that? Where's this notion of a manifold come from? It's fairly old. Maybe the first, it's kind of in the water even back as far as like early 19th century, certainly. I'm not sure really. Maybe Euler thought about it. That's usually safe to say about anything. But Monge and these, they had definitely studying surfaces in R3 as early as the 19th century. And they started becoming interested in questions of abstraction. So it seems not unreasonable to think maybe people like Cayley thought about surfaces, maybe they thought about higher dimensional surfaces. But the first person to really kind of give some kind of systematic idea of what a manifold was Riemann. In 1851, he put forth this idea of some sort of extended n-dimensional space. And he died fairly young, so I don't think he ever really exposed it, but the ball he set rolling was developed by others like Levi-Civita and who else? Can't remember his name. But a couple people. There were many authors probably, but by the time Einstein needed it in the early 20th century, it was already a well-developed subject, the subject of Riemannian geometry in honor of Riemann. And Riemann, actually the word he used for manifold, because he was German, so he used a word which is sometimes translated for us as manifold, which you can kind of understand. That's a word that was, you go back to King James, right? Manifold are his works, and right, it just kind of means many-faceted, right? And there's another word, though, that's sometimes translated from the word manifold. It's called a variety. And so the word variety has taken a more technical meaning recently. And I suppose the same is true of manifolds. But basically a manifold in the abstract is some kind of space which allows a local parametrization as a Euclidean space. I think that's a fair thing to say. It's basically, if you zoom in on some point in a manifold, you can do calculus there. That's ultimately what the point is. You could do calculus. It's locally just like Rn. So all the tools we've developed so far, implicit inverse function theorem, partial derivative differentiation, all that stuff, it's all there. But then there's also this global aspect, which is more complicated. Sometimes you can't have one patch cover the whole thing, so you need a bunch of patches to cover the whole thing. You put these things together to form what's called an atlas, which is kind of like what it sounds like. And then the atlas covers the whole manifold, and wherever you have two patches overlapping, they have to have certain consistency conditions. And maybe we'll talk about that more later in the course, but just to kind of give you a sense. But this term variety, though, is what's studied in what's called algebraic geometry. Algebraic geometry, they study the solution set to equations. And so that's essentially what I was telling you last time is the implicit viewpoint, right? But algebraic geometry's gotten more complicated, I think. But both of these notions really go back to Riemann. He used that word. The word he used, again, it's either translated as variety or manifold, which I think is interesting. So, but as a student of modern mathematics, you get the impression when you first see these things that they're just radically separated, because you can learn lots and lots of manifold theory and never really stick your foot in the door of the varieties stuff. And maybe I don't know, I think to understand varieties properly, you probably need to understand something about manifolds, but anyway, I digress. But in this course, my goal is really just to tell you the notion of a manifold embedded inside Rn. So the abstract notion of a manifold or variety, those are much more, you can talk about varieties over other things like number fields, and it's a much more flexible concept. And manifolds don't have to be subsets of Rn. Like you could have a space of matrices, which is a manifold. Okay, but it turns out that you can always kind of basically find some subset of Rn sufficiently big to make the manifold fit in there. So assuming that the manifold is actually a subset of Rn It's not the worst thing in the world to do, and that's the viewpoint we're going to take today, and for the most part in the course, except when I give you some homework problem about matrices where it's just simpler to work with the matrices directly. Okay, so let me get back to some linear algebra. What was the linear algebra I promised to do next? The theory of what? Orthogonal complements, right? So this is the major calculational tool we need to do interesting things today. Most of everything else I say is just going to be notation, but or the chain rule. So here's the deal. If I've got a set of vectors, let's say v1, v2, vk, and suppose that's a subset of Rn, then I can define the so-called let me call this set S. So S is some finite set of vectors, let's say, for the moment. Then you can define the perp to S as what? It's the set of vectors which are perpendicular to each vector in S. So let's see here. In set builder notation, what is that? X in Rn such that x dot vj, let me write it the other way around. Vj, it doesn't matter, right, because it's commutative. Vj dot x is equal to 0 for all j. You could easily define the perp of an infinite set in a very similar way. Let me not digress on that. You can show that the perp is a subspace. It's a subspace of, subspace of Rn, right? Because if you take two vectors which are both perpendicular to everything, all the v's, then the sum of them is still perpendicular to all the v's. And if you take a scalar multiple of something in the perp, it's still in the perp, because if x dot vj is 0 for every j, then c times x dot vj is still 0, right? So it satisfies the subspace test. And of course 0 is in there, because 0 is perpendicular to everything. Okay, so now, in addition, let's assume, well, I guess we don't even have to assume that. So the question is then, if this is a subspace of Rn, natural question, how to find its basis, right? How do you find a basis for the perp? All right? So let me just write down the conditions that we're trying to solve. So we're, what are we studying? We should study, we need what? We need V1, and let me just go straight to the point. The dot product can be written how? In terms of transposes and vectors. These are column vectors, right? So this can be re-expressed as, Vj transpose times x. It's a row times a column, right? So what I have is I have V1 transpose times x, then V2 transpose times x, and so forth, all the way down to Vk transpose times x. I have to solve all of these k equations in n unknowns, the unknowns being the components of x, x1 through xn. I want to solve these simultaneously, right? Now you can rewrite those k equations as a single big matrix equation. What is it? So I'm looking at x and s perp, and just to be clear. It's a matrix of row vectors, right? So, yeah. So yeah, it's like V1 transpose, V2 transpose, all the way down, Vk transpose, all times the x vector is equal to 0. Or if you understand the transpose, you could also write this as what? V1 glued with V2 glued with vk, concatenate the given k vectors in S, transpose those things, multiply by x, get 0. That's the equation we're trying to solve as a matrix equation. But this has a special note. I mean, there's an easier way to express this idea. What you're really looking at is the matrix of S, right? If we have a finite set of column vectors, the matrix of the column vectors is you just take the column vectors, glue them together in a big old matrix. So in short, x is then, so it's the transpose of that matrix times x is equal to 0, right? So there's another way I could say it. What is x an element of then? Yeah, x is an element of the null space of the transpose of the matrix. So basically, to find a basis for the perp is the same as finding the basis for the transpose of the matrix form just by gluing together the vectors in S. Simple as that. But we know how to find the basis for a null space from linear algebra. Or maybe we don't. Let me show you an example. Yeah? Let's see here. So example, let's let S equal to 1, 2, 3, 4, and 3, 3, 2, 2. I have no idea how ugly this will be. I'm not sure. We'll just work it out. So let's see here. Let's find a basis for the perp, all right? I will eventually find a marker in here that works like I like. I haven't found it yet. This one's still alive. I think this one's dead. I'm tired of it. All right. So what's the order of operations? If we believe this general derivation, we just do what? We go 1, 2, 3, 4, 3, 3, 2, 2. That's those vectors rewritten as row vectors. That's the that is what S transpose looks like. So, and how do you find the null space of this? Right, you do row reduction, right? So we do like what, minus row 2, minus 3 row 1, which gives me what? 0. 3 minus 6 is what, minus 3? 2 minus 9, minus 7. 2 minus 12, minus 10, right? Let's see here, clean it up. I hate fractions, so what I'll do is multiply the first row by 3 and the second row by 2, just to make myself avoid adding fractions, because I know what will happen if I add fractions today. Let's see here, 6, 9, 12, and also just to remind you, you can do it. Let's see here, minus 14, minus 20. Now I can add row 1 plus row 2, right? 0, minus 5, minus 8, 0, minus 6, minus 14, minus 20. And there you go. I mean, that's essentially it. I mean, I can rescale it, right? To get to the reduced row echelon form, one more step, right? So row 1 divided by 3, row 2 divided by minus 6, what do you get? 1, 0, minus 5 thirds, minus 8 thirds, 0, 1, 14 sixths, and 20 sixths. So what does this calculation show you? What does it mean? If you have vector x1, x2, right, x3, x4 in the what? In the null space. Well, let me just forget the null space. In the perp, right? What does that say about it? This calculation above shows me something. From linear algebra, I know what it shows me. This reveals a linear dependence between the components, right? This first one tells me that x1 is equal to 5/3 x3 plus 8/3 x4. And this one tells me that x2 is equal to minus 14/6 x3 minus 26 x4. Of course, you could simplify those, but oh well. Yeah, so we can use x3 and x4 as the parameters for the null space. But the basis for the null space, which is what I'm after, right? The basis is what? If you look at it, we've got x3 times what? X equals to, let me just get straight to the point. X is equal to x3 times what vector? x1 has 5/3 of those. x2 has minus 14/6 of those, right? x3 has 1 x3. x4 is 0. Plus x4 times what? 8/3. How many x4s are there in x2? Minus 20/6. Sorry if it's bothering you. I haven't reduced that to 10/3. 10/3. It's too late. I'm committed to it. All right. x3 is 0. And then 1. Oops. So I could call this let me call this W1. Call this thing W2. You can easily check that W1 is perpendicular to the given two vectors, as is W2. Is it true? I mean, check my answer. If you take the dot product of W1 with 1, 2, 3, 4, what do you get? Five-thirds minus 28/6 plus 3. And likewise, you can check the dot product of this with, and if you check the dot product of W1 and W2 with those two vectors, you should get 0 if you did the calculation right. Now, I might be able to guess vectors which are perpendicular to this given pair, just by tinkering. I don't know, maybe. Let me show you another example where I don't need to calculate. Find the perp for s equal to, let's say, 1, 1, 1, 1, 1, and 0, 0, 0, 0, 1. So basically, to find a basis for the perp, I just need to find linearly independent vectors which are perpendicular to both of those vectors. So what are vectors which are, and how many of them do you expect? This is a subset of R5. So here's a guiding theorem. The guiding theorem is as follows. S perp, direct sum with the span of S, is equal to Rn. In this case, R5. So there's always this complementariness of the span of a given set of vectors and its perp. They give the direct sum of these two things fills out the whole space. That's the way it works. Okay. It takes me a little while to prove that, but I will prove that in linear algebra, not in here. Okay, so what's the basis for? You can say S perp is equal to the span of what? I'll start the guessing. I will begin the guessing with 1, minus 1, 0, 0, 0. Why calculate when you can guess? Right? Is that perpendicular to both of those? Yeah. What's my next? 0, 1, minus 1, yeah. Okay. 0, 0. Right. I think that'll do it. Are those linearly independent? Yes. Are they nice? They're nice for us to guess. They're not nice to work with. If you actually want to do calculations, it's in your best interest to find an orthonormal basis for your subspace. These are not orthonormal. First of all, they have length 2, square root of 2, each one of them, right? And also, the dot product of this and that is -1. The dot product of this and that is -1. But you could take these and you could run them through Gram-Schmidt and produce an orthonormal basis if you wanted to. Okay. So anyway, that's how we calculate the basis of the perp. That's how we find a basis for the perp. Everybody clear on that? Does that make sense? I'm going to move along then. Now, I've done this in Rn just to avoid some annoying extra notation, because we're not going to work in Rn so much for the rest of today. We're going to work on tangent spaces and normal spaces. And the tangent space and the normal space, we want to think about the point dependence. All right, so this thing we've been doing in Calculus 3 and in here to a certain extent already, we've been abusing this correspondence between the point and the vector, right? A vector from the origin corresponds to the point, right? So sometimes I'll freely interchange between it being a point and being a vector, and I say it's just a matter of emphasis. All right? If I'm going to have an honest-to-goodness discussion about tangent spaces and normal spaces, I can no longer make this identification without doing damage to the discussion. So I need to invent a notation which clearly distinguishes between the point of application and the vector. Okay, so and here's how you do that. So the total tangent space at the point P to Rn, all right, what's that going to be? That's going to be the pairs P comma V, such that V is an element of Rn. So in my notes, in my current notes, I've also denoted this V sub P. Basically, it's the set of all vectors attached to P. So, in physics, we'll be like, well, you've got this vector here at point P1, and if you just take it, right, and over to here, then you've got this vector at P2, right? And if they have the same vector part, then we identify them. No longer. We can distinguish them. This one is P1 comma V. This one is P2 comma V. These, I'm trying to say they have the same vector part, but they have different points of application. Make sense? So the only way you can ask if they are equal, right, is if they're at the same point. So we can define how to add and scalar multiply and even take dot products and norms, all that good stuff, at a given point. Let's do it. So definition, if, let's say, P comma V, P comma W is an element of the tangent space at the point P of Rn, then define as follows. So P comma V plus P comma W is equal to, and C times P comma V is equal to, all right? And what are we going to have here? Yeah, P comma V plus W and P comma CV. So we just do the addition and the scalar multiplication on the vector part here. There is a danger for ambiguity here, right? If you're thinking about Rn cross Rn, this would mean something else, right? You'd actually multiply C in both things. But here I'm talking about, again, the addition in here. And then what's the norm of, say, the vector P comma, well, first of all, let me do dot product. So P comma V dotted with P comma W, what would that be equal to? Yeah, V dot W. And what's the norm of the vector V attached to the point P? Yeah, okay. I think you guys get the idea. And so, again, it's context, right? So, in the context of working with a vector based at P, this is how we define the addition, scalar multiplication, dot product, and norm of the vectors, okay? All right. So now let's go back to the idea of a tangent, of a manifold, right? Think about a manifold in Rn, right? So roughly speaking, some sort of picture of it. I always just go back to the picture of a surface because I'm lazy, but it would be something like this, you know? And again, we can either describe it parametrically or implicitly. It kind of depends on which viewpoint you want to take as primary. And then you can ask the question, okay, so I've got this manifold embedded in Rm. I usually use an M for it sometimes. And I can ask the question, what would the tangent space at a particular point be? You know, what would the tangent space at the point P to M look like? How would we define the tangent space? What should that mean? How did you define the tangent space to a surface in Calc 3? Can you remember the definition in Stewart? If you use Stewart. I can't, because I never found one. What's that? Not really. I mean, I want something more. I mean, it does have to do with the gradient if you have a function around. It's true. I mean, we can calculate it in terms of the gradient if it's a graph. True. But more primary, like more basically, what should we think of the tangent space as being? I mean, the set of all tangent vectors, right? What is a tangent vector? Well, I mean, how about a curve? You think about all possible curves through the point and all possible tangents to those possible curves, and take the union of all those things, right? If those glue together in some sort of meaningful way to form a plane, to form a subspace, then I would like to call that thing the tangent space. Now, yes, but that would be distracting. So, I mean, many things can be given a manifold structure, but it's not helpful to the current discussion to think about that. So I think of the tangent space as being a hyperplane, right? And so you have all possible curves, and so they're tangent vectors. You know, they fill out some kind of plane, and that plane is what we call the tangent space. It's all possible tangents to all possible curves through that given point in the manifold. I can be more precise. Let's see here. If P is an element of M, then the tangent space to P at M is equal to the pairs P comma V, such that what? V is equal to gamma prime of 0, let's say, where gamma is some mapping from the reals to M, for which, and this is just our convenience, gamma of 0 is equal to P. You could set the definition up with the parameters going to time, the parameters matching up to P being something other than 0. 0 is just a convenience of X position. And if you wanted to, you could take the domains being smaller than the whole reals, but again, just for convenience of X position, I'll take the domain of the curves to be R. Right? So, theorem, the tangent space to P at M is a subspace of TP-Rn for M subset of Rn. But if you're paying close attention, you might have noticed that I haven't quite, maybe I defined loosely last time what M is, what it means for M to be a manifold, right? But this claim begs a question. What do I mean M is a subset of Rn as a manifold? I mean, what does that mean? This theorem is true either for M being the inverse image of some constant vector C, where the rank of the level function is equal to n minus, I need the dimension of M. Well, I haven't used k yet, have I? No, so n minus k. Or you could say that's equal to M. Or it could be that M is equal to the image under some parameterization. I think I called it big X of D for in the rank of the parameterization is equal to k. And my assumption here in saying this is that the point P is, just to keep it simple, I'm assuming that these have constant rank over the whole thing. I don't want to think about manifolds that have like 2 dimensions one place and 3 dimensions somewhere else. That would make me write a lot more. You could think about those kinds of things, but people usually study manifolds of equal dimension. All right, and so I'm assuming here that P is some point in the solution set of f equals to C, or it's some point which is mapped to by this mapping x. Now, what's the difference between x and d? F, right? F is a function from Rn to what? I think n minus k, because I need n minus k. I need n minus k conditions in order to leave me with k dimensions. N minus k is equal to k. N minus parentheses n minus k is equal to k. And x, on the other hand, is just a mapping from some parameter space D, which is a subset of Rk, to Rn. Yeah. Sometimes I call this the hands-on approach. This is the hands-off approach. Like, hands-off approach is like, I don't know, the manifold is a solution set to some equation. So if you want to figure out if a point is in there or not, plug it into the equation, see if it works. Right? That's the implicit viewpoint. Parametric viewpoint, on the other hand, is the point on the manifold. Well, you got to give me the point in the parameter space which maps to it. So, but in either case, you can show that if you have curves, right? If you have curves in the manifold, that if you have 2 curves and one has, say, velocity v1, one has velocity v2, there's another curve which has velocity v1 plus v2. And if you give me a curve with velocity v1, I can find another curve through the point which has velocity c times v1. This is all possible through the chain rule. All right? Obviously, there's something to prove there, right? I mean, how do I know that this thing so constructed, all possible tangents, all possible curves, that has the structure of a subspace? I don't think it's immediately clear that that's true. It happens to be true because of the chain rule and the implicit function theorem applied to either the patch or the level set. Those proofs are in my notes, at least for the one I think which is more subtle, which is this viewpoint. If I have enough time, I'll show you that. I don't know if we do, though. I was too busy talking about Trump today. Sorry about that. We shouldn't trade Trump for math. It's not a fair trade. The United States will be judged for its various transgressions, but this math is still going to be good. You're a fan of what? A good community? Oh, comedian.
My computer science professor said he wants Trump versus Biden in the general because he can't be a president. At least he'd be entertaining.
Yeah, Trump versus Biden would be amazing. Yeah. Yeah. I've thought about that. I actually think Biden is more likely to win against Trump than, say, Hillary. That's my personal opinion. Yeah.
Because Trump would be like, look at that face, and then she'd be like, what? And then she'd be like, I'm not.
I mean,
low
yeah.
voting for her candidates.
Oh. Let me see here if I can. So let me let me go on is what I should do. So let's look at an example. That's probably helpful. Let's look at m, which is the function defined by x, y, z, t, s. Oh, t and s are bad choices. I don't want to use numbers. Numbers are awful. I need some other letters. Alpha and beta. Yeah, I'm not giving you enough time to say something about 7. Suppose that this is equal to, I don't know, x squared plus y squared, comma, y squared plus z squared, comma, alpha beta. There. That's weird. Weird enough. So there's a level function, and so I'm not done. M is equal to, let's say, f inverse of what? I'll say 1, 4, and I don't know. Fine. You can have your way. I'll give you that. I'll give you that 7. So,
you know, in putting it up there, you now define my reasoning for there's no 7 up on them or whatever. So I'm only helping you out.
all right. Is this a manifold? And if so, what's its dimension? So let's see here. What's f prime? So I've got 2x, 0, 0. Oh, sorry. How many? Yeah, that's fine. Sorry, I'll get it eventually here. So x is the first variable, then partial derivative with respect to y, 0, 2y, 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 0. What's the z derivative? 0, 2z, 0, and then alpha derivative, 0, 0 beta, 0, 0 alpha. Partial x, partial y, partial z, partial alpha, partial beta columns. So we've got a 5-dimensional ambient space, 5-dimensional Rn, right? And we have 3 equations, right? So we expect that this probably defines a what? A surface, a 2-dimensional manifold. Provided what? Yeah, we need the rank of f prime of p is equal to 3 for each p and m. So let me just say that we're just going to take this intersected with set of such p, okay, as this. I don't want to, I mean, for example, x not equal to, for example, we could look at a point. Let's pick a particular point. Let's look at the point. Let's study the particular point. Let's study the point 1, 0, excuse me, other way around. 1, 0, 1, comma, 0, comma, no, excuse me. I will get it right eventually. 1, 0. So what I'm trying to say is let's look at the point x equals to 1, y equals to 0, z equals to 1, alpha equals to 1, beta equals to 0. Let's look at that point, and let's try to let's find the tangent space and the normal space to the manifold at that point. That is a three-dimensional. There are three independent equations there, so the manifold should be two-dimensional. Yes, sir?
That is our P, then what is the 147?
That's just what the equations have to work out to. So it's the, yeah. If you took different C, you'd get different manifolds. Like you.
Oh, it's not C.
Yeah. You could say this is the level C manifold. If I change C, I get different manifolds in R5. So C is a parameter on some sort of family of manifolds, for what it's worth. But all right. So let's see here. So there's a little proposition I need for us to guide our thinking. If f of gamma of t, right, is equal to 0, then what? Then f prime of gamma of t times gamma prime of t is equal to 0. That's a chain rule. What does that say about, what does it say about, in particular, if gamma of 0 is equal to p, then what? Then gamma prime of 0 is what? Well, fine. It's in the null space of f prime, right? Yeah. More to the point, gamma prime of 0 is an element of what? It's an element of the perp of the. So if you look at the column space of the f prime of gamma of 0, which is f prime of p, it's in the perp to that, right? No, that's not the right way to say it. Sorry, guys. I'm having a moment of stupidity. I think that's the chain rule. Just a second. Let me just write out something. So f is what? It's f1, f2, f3, right? There's 3. So f prime looks like what? F prime looks like it's actually the gradient of f1 transposed, the gradient of f2 transposed, the gradient of f3 transposed, right? So, this of course is what? This is gradient of f1, gradient of f2, gradient of f3, transpose, right? So when I have this, I'm actually saying what? Gamma prime of t is an element of what? The null space of what? Which is also known as what? It's the perp of what? By what we discussed just a little bit earlier. Now, I just wrote it out for 3, but it just as well works for more equations, right? The point is, the tangent vector to a manifold defined by a level equation, the tangent vector has to be perpendicular to the gradient of each one of the component level functions. That's That's the geometry here. So and also, I'm sorry, guys. My mind is not clear today for some reason. Notice the tangent space to P. I blame you, Joe. You usually come to ask me questions before class. It keeps me from preparing. Whenever I start preparing for class, it just goes downhill. It's all your fault. You gave me time to prepare this morning. So the tangent space to P at Rn, it's going to be equal to the tangent space to P at M, direct sum with the tangent space to P at M perp. Okay? That follows from the theory of orthogonal complements and the fact that the linear algebra is the same, even though we've attached a point, right? But when you get right down to it, the formulas we defined over there for the tangent space of P, they're the same, right? So everything I proved in linear algebra about orthogonal complements just as well comes over here. And this perpendicular space is what's called the normal space at P to M, so-called normal space. All right? So for the example I'm looking at right now, the normal space would be something like, you just take it's the span of the first function at P. Oh, sorry, this isn't going to work. What do I have to do? P, comma, the gradient of F1 at P, comma, P, gradient of F2 at the point P, comma, P, gradient of F3 at the point P. So the normal space is three-dimensional. The tangent space should be two-dimensional. The normal space is easy to find if you set up the manifold as an equation of a level equation implicitly. So the normal space I can tell you right now is what? P comma, you guys give it to me. P comma, give me the vector. P comma, give me the vector. And now I'm going back to the specific P. All you have to do is plug in x equal 1, 0, 1, 1, 0 into the gradient vectors, which are the rows, right? So what's the first thing? 2? Yeah, 2 and then zeros. Very good. Then what's the next one? Okay, yeah. Very end. Okay. Now, so, my temptation, of course, is to go back to, since I just wrote this definition, I was about to do something foolish. I was about to go to try to find you some curves on the manifold to differentiate them to discover the tangents to the tangents in the tangent space. And we can still do that, all right? But it's probably easier here to just calculate the complement to the normal space. See, if another bit of linear algebra, which is important to know about as you do calculations here, is if I have V is equal to W1 direct sum W2, this just means that the intersection of the two subspaces is 0, and that they add anything in the vector space can be reached by adding these two things together, actually uniquely so. But this says that supposing that these are, we've got the inner product here. So W1 perp is equal to W2, but it's also W2 perp is equal to W1, as it turns out. And the perp of the perp is back where you started. It's kind of like, transposing. So given that this is the normal space of P, what's the tangent space of P look like? And by the way, so like the first section I have, I was reading the notes again because Joe didn't ask me questions this morning, which of course has ruined this lecture. It's all his fault. But Oh, good comeback. Let's see here. So the first section I have, I forget to put the p next to vectors. I've dropped the point of application in like the first section, but then I'm more legalistic about it in the second section that you read. So you can see, as the chapter progresses, I become more careful about remembering to put this annoying point of attachment wherever it should be. So what are these here? My point is, you can look at the three vectors we have here, and we can just pick ones that are perpendicular to these, right? What's going to be perpendicular to these three vectors? Can you tell me? I'm going to do the easy one. 0, 1, 3 zeros, right? You can check that that's perpendicular to all three of these, right? 0, 0, 0. What's my other one? Yeah, the mirror of that, yeah. And there you go, that's the tangent space, which is two-dimensional. The tangent space will be the same as the dimension of the manifold. Basically what the tangent space is a local linearization of the manifold. Okay. It's actually the graph of the linearization with the appropriate preamble. Can you guys show me how to get these two vectors as the derivatives of particular curves on this manifold? Can you tell me what would be, for example, can you give me a gamma 1 of t, which is a subset of this manifold? So to do that, you need to give me formulas for x, y, z, alpha, and beta. And I want x squared plus y squared to be what? 1. How about this? Cosine t, sine t. That gives me x squared plus y squared equals to 1, right? And at 0, it gives me 1, 0, which I need, right? What should I make z? I need z to be 1 this time, though, right? So, is it still? Can I still do? Oh. Okay, yeah. So cosine t again, yeah. I can only use t, by the way. I'm parametrizing a curve in 5 dimensions, which lies on this 3-dimensional space. The game is to make these values come out with the parameters, right? So you see I have x squared plus y squared equals to 1. I got y squared plus z squared equals to 1. And now what else do I need? I need alpha, beta to work out to, what was it? 7. Thanks, Joe. Oh, 4. Oh. Ew.
You did the 4.
I did do that. Oh. Oh. Yeah. That's unpleasant. Very good. But does that change any of this? Any of that? So that's funny. So this didn't. I kind of understand your question more, Bradley. You're like, what does that have to do with anything, right? Yeah. I see your question. I mean,
Maybe we should have checked that actually.
what's that?
Maybe we should have checked that F of P was.
Oh, that I actually have a point which is. Oh, that's true. F of P is not equal to 1, 1. You can't have 7 either? Oh, man. I put 0 here. All right, fine. Let's make the example make more sense. There we go. Yeah. Oh, yeah, I'm only allowed to do this. In your homework, you're not allowed to do this. Unless...
This makes that homework easier. Like, this one doesn't make sense.
Although... well, you actually, I mean, it depends. Sometimes you're allowed to do this. It kind of depends. well, I mean, I don't know. Okay, so cosine t, sine t, sine t, cosine t. Now I have x squared plus y squared equals to 1. I've got y squared plus z squared equals to 1. 1, 0. Oh, just 1, 0. Does that work? Okay. And then the, let's see here, the other one you could do, gamma 2 of t, another curve you could do would be what? How about 1, 0, 1, 1t? Let me think about that for some more. I want the alpha product of alpha and beta to be 0 though, right?
Yeah, so you could be 0 t, or t 0.
But I also want alpha to equal to, I want alpha to equal to 1 at p, right? I mean, I want at t equal to 0, I want to get out 1. So I think you're right. I can put 0 here, right? And I can do what do I want again? I'm sorry, I keep losing track.
Well, can alpha ever equal 1 then?
Oh, alpha.
It has to be something that can equal 1 for alpha.
Oh. Oh, so the other way around. I want something like 1 plus t, 0. Would that work? So then alpha is equal to 1 plus t, and beta is equal to 0. So alpha beta is equal to 0. But when you put t equal to 0, you get alpha equal to 1. I think that's right.
So why are we doing t equal to 0 always?
Oh, just to go. That's just a convenience. I want to have. I want gamma 1 of 0 equal to gamma 2 of 0 to equal to 1, 0, 1, 1, 0. In other words, p, right? And then with that in mind, what's gamma 1 prime of 0 and what's gamma 2 prime of 0? What do you say? 0, 1, 0, 0, and gamma 2 prime was what? Look familiar? It's no accident that is exactly what we guessed over here. See, because you can either calculate the tangent space by directly finding curves that are on the manifold and finding their actual tangent vectors, right? Enough so that I get the needed dimension. You know, I know it's two-dimensional from the other counting. So once I have two curves with independent tangents, I know that's going to give me a basis for the tangent space. Or, if I know the normal space, I can find the orthogonal complement of that to get the tangent space.
So what was that method?
What was that?
Yeah.
That was finding two curves, gamma 1 and gamma 2. They're two curves that lie on M, right? Like this was gamma 1. That was gamma 2, let's say. And so the tangents to those fill out the tangent space because there's just two-dimensional.
Okay.
See the difference in reasoning?
Find as many curves as there was dimensions to the tangent space.
Yeah, they have to be independent curves, of course. I mean, some curves, if there are lots of curves that give the same tangent vector, well, or collinear tangent vectors, those won't help us. But I mean, you see how different the method of calculation is here? And so how do you find the normal space? How do you find the tangent space? I think it depends on your starting point, right? My argument would be this. If the manifold is presented as a level surface kind of thing, it's simple calculation to find the normal space directly, right? Assuming that the instructor of record has given you a point which is actually a point on the manifold, stuff like that, you know, assuming the problem is set up correctly. It's as simple as calculating the gradient vectors and sticking in the point. There you go.